Today's lecture is a continuation of Chapter 7, Slope Stability. We took before a very quick introduction about the different types of slope, whether natural, man-made, the shape of the slope, the shape of the failure surface of this slope, and we said that normal shapes is not just any of these presentations. It is something like a combination of many slopes together, working together. Now we go to something called the factor of safety. What is the factor of safety? What is the factor of safety? First, we have to understand what is the factor of safety. If I have a slope like this, and this slope is going to fail, how much it is near to failure? Is it going to fail now, or maybe it will fail in the future if something happens, if an additional loads come or something? How can I know? Then there should be, as an engineer, I should have a method for judgment to say that this slope will fail anytime now, or no, it will not fail even if anything happens in the future, or it may fail in the future, I don't know. So how to do this? I should have something called the factor of safety. What does this factor of safety depends on? It depends on the forces. If I have forces, imagine that you are standing and somebody next to you is pushing you, and there is another person on the other direction pushing you in the opposite direction to keep you in place. So this is really what is your factor of safety. If somebody is pushing me with a force 2 and another one keeping me in place with a force 2, so 2 minus 2 is 0, then I will be in place. But if somebody is pushing me with a force 10 and somebody is trying to keep me in place with a force 5, then I will fall, because 10 minus 5 is 5, then I don't have any factor of safety. Nevertheless, I will fall. But if the opposite, if the person who is keeping me in place can carry up till 10 kilos or 10 tons, and somebody is pushing me with a force 5, then I have a factor of safety of 2, because this person who is pushing me to fall down with a force 5, there is another person resisting him, but he can carry up till 10, so he will easily carry the force of the 5. And if somebody else come again and try to push me with the other person, and they both push me with a force of 5, he can still carry this double forces, which is 5 and 5 to be 10. So this is my factor of safety. Factor of safety means what is the force that is keeping me in place compared to the force that wants to let me fall down. So this is what is the factor of safety. Factor of safety in case of soil and in case of this shear strength parameters and these shapes, then the factor of safety will be tau divided by S. Tau is the shear strength, which is the maximum that the soil can carry. The soil can carry a maximum force of so and so. But there is a force acting on the soil with a certain value. What is this force? If I have S equal to tau, then my factor of safety will be 1, because there is an external force acting on the soil, and the soil can carry this external force without any problem. So I don't have any factor of safety. I can carry the force that is coming to push me. But if I can carry more, then I will start having a factor of safety then nobody can just let me fall because I have a big factor of safety. What is the value of tau? This equation, by the way, is the same equation that you have used in the report for the calculation of the shear strength parameters. So tau is equal to sigma n multiplied by tan phi plus c. From this equation, you calculated the c for the soil, and you calculated the phi from the soil, but you calculated in a graphical method. So now these are the two factors. How can we calculate this? If I just look at this, imagine that this is a circular part, and the soil here wants to fall down. So this is the force that is causing this slope to fall. But what is preventing the slope from falling? What is preventing the slope from falling is the friction along this line. If there is no friction along the line, then this will fall. But if you have friction, and the example of the friction, if you have a small kid and that he is, you know, that the slider that we have in the playgrounds, small kids going up and sliding board, and they go from top to bottom. They slide on the surface because actually their own weight will exert force that is more than the friction between their body and this this machine or this surface. But if I let somebody to slide along a rough surface, what will happen? He will not slide because this surface is rough. He will not slide on this surface. So this is exactly what we are going to see here. If there is friction here, this friction will prevent this body from falling. But if this friction is small and this weight is high, then the higher weight will be more than the friction, and this body will fall. So how to calculate these forces? We have two types of forces that we need to calculate. These two forces, we are going to discuss it when we check the next section of the lecture. But let's now go to the calculation of the factor of safety. We calculate two things. Something called MD, which is M driving, and MR, which is M resisting. M driving is the force pushing the slope to fall. M resisting is the resistance of the slope to failure. I divide both together to get the factor of safety. It depends on the type of the slope. There is something called infinite slope. If I have a slope like this, and I have soil on top, this is hard layer, and this is a little bit soft soil, and this slope is extending in the perpendicular direction a very long distance. I can just check it as being an infinite slope. Why? Because all of this layer with the thickness h can move. Nothing will prevent it unless there is enough friction between this top layer and this line. So if I have enough friction, then this layer will stay in place. Sometimes you might have seen videos for something called mud flow. So you find that something like a mountain that is moving down to the bottom. What is happening? You have a top soft soil, and this soft soil is very, very soft and it does not have any shearing resistance, so it starts to slide on the stronger soils below. So it will start to move down here. So in this case, we say that this is an infinite slope because it has no limit. It can take any area and fall down. Modes of stability analysis. Now we are going to study finite slopes. Finite slopes, it is not just a layer that is extending on the top. No, it is a portion of the slope that is going to fall. A portion like this one here, this is a portion. If I say that this is going to fall, it is a portion. It's not the whole soil. It is not all of this layer sliding on this barrier if it is inclined. No, it is a limited part that will fall. So there are some methods for calculating these finite slopes. There are graphical methods and there are charts for doing this. What we are going to concentrate on is the graphical method. By the way, this is very complicated, and the method of analysis, you will find lots of theories to calculate these, but they are very complicated and they are time consuming. The easiest way, of course, before a long time ago, we did not have very powerful computers and things that would help us to solve a problem in a limited time. So usually they prefer for any complicated problem to try to solve it graphically, because if you solve it graphically, then the effort will be less. So a long time ago, they presented many graphical methods for solving these slopes, and of course these graphical methods are based on equations and theories presented by these people. The first one is circular arc method. Circular arc method, it means that I'm assuming that my failure surface will be a circle, a part of a circle. It is not ellipse, it is not any curved shape, it is a circle. So if I have a circle, it means I can have a center for this circle. So imagine you have, this is the line, that is the slip surface or the surface where you will have this failure, where this failure will happen. What is the forces? I need your contribution here. What are the forces that would cause this surface to fail or to fall? And what are the forces that are preventing this surface from falling? Can anybody of you now think of this? I need, based on what you have just heard, just try to imagine. I'm just going to repeat what I said. What I said, that for this to fall down or to reach the failure case, it should move. To move, it will move along this line. So the bottom part is stable, it will stay as it is. But this portion will start to slide. What are the forces that is causing this portion to slide? It is shown, by the way, but you have to think of it. If this portion wants to slide, what is going to push it? What are the forces? Yes? These forces, but what are these forces? These red forces, they are the forces that are pushing. The own weight, this is the first one. So this W is the own weight of this wedge. It wants to fall down. So this wedge is pushing me. But I said that it is going to move along this circle, this part of circle. So this is the center of the rotation. So it means that I have a force that is pushing this force is equal to W multiplied by x1. x1 is the arm of this force, this rotational force. So W multiplied by x1 is a force trying to push the slope to move down. This is the first one. But I have also distributed load on top of here. So this distributed load, I can remove it and put instead of it a concentrated force. This concentrated force also multiplied by this arm would give me another force. This force is trying to push the slope down. So this force is pushing down, this force is pushing down. So what is preventing? What will prevent? The friction. So where is the line of action of this friction? The line of action is here. This is the interface between the part that is going to move and the part is staying. So at this interface, there will be some friction. Imagine that this friction is just these small lines. These are the frictional force. So the total friction is what? The total friction is this small force multiplied by this arm, plus this small force multiplied by this arm, plus this multiplied, and so on till I reach the top. So all of this is the frictional forces that is preventing this line from, or this portion from sliding. So I now have something called M resistance, and I have something called M driving. M driving is the summation of all the external forces or the internal forces that may cause motion. So it is W multiplied by x1, this force multiplied by x2, and any additional forces. If I put somebody came and stand here, so it is his own weight multiplied by this distance also, this additional force acting on this slope. Then I go to the part of the friction. What is the frictional force? It is tau. Tau is the internal friction of the soil. I just multiply it by the radius and then multiply it by the full length here. If I multiply it by the full length, then I get a summation of all of the forces from this point till the end of it. So this is MR and this is MD. If I divide MR by MD, then I get the factor of safety of this slope. By the way, this is a case, I will just say it very quickly because I see that to understand it, to understand what I'm going to say here, you need to understand fully what I said here before. Suppose I said that the friction is this, all of this part. Suppose I get a shovel and I start digging here till I reach this point. It means that is my friction still working as before, or I already lost part of the friction? So back to our calculation. If I have here something called tension crack, you remember if you go to any field, you will find, if you have clay, you will find that this clay is cracked. This tension cracks happens with clay a lot. If you have clay and this clay starts to dry, once it starts to dry, we have a tension crack. This tension crack goes to a certain depth. Then in this case, my friction will work from here, all the way here, till I reach this depth. Once I reach this depth, the tension, the friction will not continue because it will find an easier way. Instead of going on this line, it will be, this portion will be separated along this crack. So I don't need this friction. So in this case, if I have a case of tension crack, then I should calculate the length up till the depth of the tension crack. I should not go to the top of the surface of the soil. To solve this problem, it is a little bit complicated, and it will need lots of calculation. So people who studied this presented something called the Swedish method, or the method of slices. The method of slices depends on, instead of studying this as a bulk, they divide the soil into strips next to each other. By the way, this is one example that usually come in the exam. Any final exam usually includes a problem to solve based on this method. And so it is very important to understand it and to solve it by hand, not just to understand. There is a formula sheet, and I usually, even if I don't give you a formula sheet, I give you the equation that you are going to use in this problem. So this problem, they studied what? They, instead of studying all of this portion, they said, no, we are going to divide it into small slices. That's why it's called the method of slices. So I will study this slice, and I will study the stability of this slice. What is the stability of this slice? This slice has an own weight. This own weight has two components. One component driving the soil below, and one component is vertical on the soil. So this component is the component that is driving the soil below. So I need to calculate the weight, the full weight of this slice, take the portion of the soil in this direction, this portion of the load in this direction, this portion is the driving load for this slice. What is preventing the soil from movement? What is preventing is the friction along this small area. So I get the tau, and I multiply it by, I take the friction along this small area. This friction will come from two components. It will come from component depending on the phi of the soil, and it will come from a component depending on the C of the soil, because the C adheres the soil to each other, and the phi induces friction in the soil. So my full friction is the sum of the friction and the cohesion of the soil. So I have here to divide my problem into slices. This is 1, 2, 3, 4, and so on. All of these are my slices, and I start to study each slice alone. I get the volume of the slice. From the volume, I calculate the weight. From the weight, I get the component. The weight is vertically down, so I have to resolve this force into two perpendicular forces, one tangential and one perpendicular to the base. Once I get this tangential force, this will be my driving force, and then I have the friction from the soil below. To simplify this, we do it, as we said, in a graphical way, and we put the values in this tabulated form. For each slice, what is h? H will be the height of each slice. Of course, it is the average height for each slice. Then I have B. What is B? B is the width of each slice. Usually I divide it into equal slices. So I expect that this B will be equal from here to here. All slices have the same width. And then I get the angle phi. What is the angle phi? I want you here to differentiate between two things. This is not phi, this is theta. I want you to differentiate between theta and phi. Phi is the phi of the soil. But theta here is something related to each slice. Each slice has a different angle. Here it is written as I think it is written alpha, but it means the same. If I am studying here, then this will be my theta. This value theta for this slice is different to the one next to it and the one next to it. By the way, in solving this, usually it is given in the problem, but in normal life you have to be able to calculate it, because I have here a vertical force and I want to resolve this force with the knowledge of this angle. What is this angle? It is the value between this force, the value of the angle between this force and the perpendicular to the tangent, to the base. So I just, this is my theta. So I start here putting the theta of each of these slices. You will see an example for this and you will be able to understand it. Then I need to calculate the weight of each slice. To calculate the weight of each slice, I need to multiply the volume of each slice by the own weight of the soil. This is something easily calculated. Then I need to calculate W cosine phi. W cosine phi is the force that is driving. It is this one. So this, according to this table, phi is this angle, because W cosine, this is W, and if I get W cosine phi, it means that this is the force that I need. So this will be my phi. So this is the value of phi. So I multiply the weight by cosine phi to get the component of force in the direction causing sliding. And then I get W sine phi. So W cosine and W sine. Depending on which one I'm going to use in the sliding, I will tell you exactly where is phi, theta. Is it this one or this one? I will just go to this equation. You will find that whatever on top here is the force causing the sliding. So the force causing the sliding, it means that this theta, or the value of theta, is the value causing the sliding. Anyway, when we go to the example, it will be very clear, but you have to know that in any analysis, W cosine, you are using the angle next to the force. If this is W, then this will be W cosine, this is W and this is theta, then this is W cosine and this is W sine, and so on if theta is the other one. Anyway, you are going to do this for all slices, and then you are going to get the sum of all of these values and the sum of all of these values. So these are the components of W cosine, and this, the summation of W cosine, and this is the summation of W sine. I will take this, use the equation for the factor of safety. In the equation of the factor of safety, I have, this is the equation that you are going to use. I use the summation of W cosine, and here the summation of W sine. It means that the W cosine is the forces causing resistance So the force is causing resistance. It means that this is the one, because this is causing resistance and this is causing driving. So this is your phi. So finally, the angle theta is the angle between the vertical, the force, the vertical force, and the vertical component to the tangent. So this is the value of phi. I just substitute in this table to get the factor of safety. I may add the effect of the pore water pressure if I have pore water pressure, because you know that we need to work on the value of the effective. You remember from previous studies of total and effective stress, we said that when we study forces in the soil, we study the effective force, not the total, because I don't want the portion of the force that is carried by the water. So in this case, this will be my factor of safety. It's an equation. I just substitute in this equation, but if I going to use this equation for the full mass, it will be difficult. So it is easier for me, or more accurate for me, to divide my forces into slices, and I calculate this tabulated form for each slice, and then I get the summation for the W cosine and the W sine. Use these summations, add them in the equation, you will get accurate analysis for your case. Of course, in case you have a tension crack, then you have to reduce the effect of the tension crack on the equation. There is another method. This other method, the one that we have studied, is called the method of slices. This is the one that you have to study by heart, because this is the one that you are going to use in your course, and you have to solve problems using this type. But there is many other methods, but from these other methods we have something called Bishop's conventional method. By the way, the previous method was presented by Fellenius, so sometimes we call it Fellenius method, or we call it the method of slices. But the other method is called Bishop method. But take care that Bishop presented two methods. So it is Bishop's conventional method, the normal method of Bishop. What is the difference between this method and the other method of slices? The difference is that they study the stability of each of these. It is, you have slices, but in this case you may have bigger slices, and you study the stability of these slices using graphical presentation. This is all what you need to know, that Bishop's conventional method, he studied slices, but a little bit bigger slices, and these slices he studied the stability of each portion using this graphical method. If I have a body, this is a body, and this body is subjected to few forces. One force from up, one force from down, and one force from the side, lots of forces. If I made graphical presentation for these forces, I started with the first force, I draw it like this. So this first force is the force of the weight, and it goes like this. And then I have another force here. Then I draw this force here. If this force will take this body from this point to this point, and the other force will take this body from this point to this point. To be stable, I have to have another force, a third force, that would come from this point to this point. In this case, So one force will take me down, one force will take me to the side, one force will take me back to my starting position, then I'm at a stable position. So this is exactly what is behind this method. This method, he takes each body, he put the forces on the body, and the force that will cause stability will be the force that will close the shape. Whether the shape is triangle, rectangle, any shape, the force that will cause the force and the direction. If I have here a force in this direction, this force equal to this value, it will cause stability for this portion. And he studied this for this one, this one, this one, and so on, and presented this for all of these slices. And there is also a presentation, but just to think how complicated is this one. These are all, this was your previous table for the method of slices. The maximum that you are going is to W cosine theta and W sine theta. But look at this table to study. You will find that you have W cosine minus W R minus, this is another force, sec and cosec, and tan and cotan. It is a little bit complicated, but of course it is complicated because it is a little bit accurate more than the other one. But for the time being, we are satisfied with using this method, and for this method and the one next to it, you have just to know that this is my equation for the factor of safety. Compare it to this one. This is my equation for the factor of safety. You will find here that it is here a little bit simplified. Here it is a little bit complicated. But was this the end of Bishop? No. He gave us a more complicated method. This conventional method, we consider it a little bit complicated. So he gave us a rigorous method that it is more accurate, but of course more complicated. Just for you to imagine, this is the equation for the factor of safety. Many levels and tan, cotan. It is very complicated, and to do it in even in a graphical way, you may make lots of mistakes. So we tend to say it is enough to work with this method. If we need to use another method for confirmation, you may use this method given by Bishop, which is the conventional method, but Bishop's rigorous method is very complicated, and it will be very difficult for us to use it in this syllabus. So we just know it that Bishop proposed two methods, the conventional and the rigorous. The rigorous is a little very complicated, so we just know it to understand it. Now we go to another part of the lecture, which is how to protect our slopes. Before we move to the method of protection of the slope, I just want to confirm that the previous method for the analysis of the method of slices is very important. You have to study it by heart. We are going to make a revision for it prior to the exams, but you will have to exert your maximum before going to the revision lecture. It is very, very important that you do this. Otherwise, you are going to lose a very big portion of the degree, because this contributes a very big portion of the problems of the exam. How to protect our slopes? Now we know that our slopes we have to think of two ways for changing the slope. If I have slope and this slope is going to fail, sometimes you find that people are covering the slope with some rocks and concrete blocks. You've seen this in many places. Does this change the factor of safety? Actually, no. Why no? Because let's see here this example. This example, we calculate the factor of safety of the slope. If I just put pieces of rocks on top of these slices, what will happen? What is the contribution of these small rocks on top of this slope? If I have here a weight W of 100, this will be how much? 1, 2? It will not affect the stability of the slope. It will not increase the factor of safety, but it will help in another way. What is this other way? This slope, maybe with time, due to the effect of rain and moving water and wind, there will be some erosion here. And if some erosion happens here, it means that the shape of the slope will be changed. In this case, I'm going to lose this slope with time. So, slope protection, you have to take this into consideration. The protection, any method for the protection of the slope, it is for the protection of the shape of the slope. It does not have an effect in increasing the factor of safety of the slope. How can I do this? I can cover it with rock. Easy, you have seen this a lot. I can cover it with agriculture. Not agriculture, planting. I can just put some plants, and the roots of these plants, of any cultivation, the roots will go inside this slope, and it will help in keeping this this slope at place. It will not affect it. I mean, if rain is going down this slope and there is some plants here, it will stay in place. But if rain is coming on this slope and you don't have any plantation, maybe with the time the soil will be engulfed, it will be taken away with the rain. Pitching, what we call in Arabic tadbish. You might have heard this a lot. In many places you find higher levels and lower levels, and between this there is slope, and they go with rock blocks and place them next to each other, and sometimes they add mortar in between. So this will be the shape. This is pitching. Sometimes they cover it with concrete slabs. You have seen this in channels in Toshki and many places, when they want to make a waterway, but it is a man-made waterway, they just go and cover the sides of this, because there is a slope in each direction. So they cover this slope with concrete slabs, so cover with concrete. Another thing is, how can I make slope stabilization? Now we go to the inside. What we were studying here was just cosmetics, something on top of the slope. I'm just trying to protect the surface of the slope. This is slope protection. But when I speak about slope stabilization, it means I want to study the stability. Stability deals with factor of safety, then I have to increase the factor of safety of the slope. How to increase the factor of safety of the slope? I can put reinforcement. If I put some rock bolts, dowels, anything that would penetrate the slope, as if that I am putting nails inside this slope. If I imagine here, you have this. This is your slope here, and I put nails here. Imagine that I just put a nail here and another one here and another one there and so on. These nails will prevent all of these slices from falling down. So it is adding to the factor of, to your factor of safety. So the first one is reinforcement support. So nails, bolts, dowels, something like this. I can remove unstable blocks. If I have, if this slope is made of blocks and I find loose blocks, if I remove these loose blocks, of course it goes without saying, my slope will be better in performance. I can put protection. What is this protection? Protection is something that would cover the slope. I will cover, imagine that I bring a steel mesh and I put it on the slope. This steel mesh will prevent any portion from falling from this slope. You will see this here. First, let's take them one by one. Rock bolts and anchors. This is a slope. This slope can fall. What will happen? You see these steel rods that is coming out of this slope? These are the end of bolts or anchors, like a long nail that penetrates the soil. I just go to this soil here, I drill a tube and I remove the soil from inside, I put this nail inside or this bolt inside and I cover it with mortar. In this case, once this mortar dries, then this bolt will be as if I'm adding reinforcement to this block. So this is the first type, adding rock bolts or rock anchors. The second one is steel rods. The same, if I hear bolts and anchors, means that I can apply a little bit of pressure to this bolt or to this anchor. But I may just put just a steel rod inside. I put, as if you are piercing the ground with some steel rods. But I have to take into consideration that these rods, if they are made of steel, then I should study their corrosion with time in the soil. I can add shotcrete. You heard about shotcrete before? This is what I was telling you. I can just cover the slope with wire mesh. This, you see these steel? These are all, it is as if I'm putting a mesh. I can leave the mesh as it is okay, but I can cover it with concrete. If I can cover it with concrete, as if I'm pouring a concrete slab with a variable shape on top of the rock. So if this is the slope and this is my concrete mesh, steel mesh, I just pour concrete as if I'm pouring concrete on top of this mesh. So I end up having a concrete slab, but instead of having a slab with a specific shape, no, it is variable in shape. It takes the shape of the rock. So it covers the rock as if I'm having a concrete slab covering the rock everywhere I go. So it is another way for for fixing this slope. This is all okay. Another method is grouting. I really do not like grouting in any geotechnical case because I don't guarantee grouting. What is grouting? Grouting is pumping concrete inside the soil. So when you pump concrete inside the soil, it adds to the cohesion of the soil and the friction of the soil, because as if you are replacing the voids of the soil with mortar. So it is something very good. But it is very good in case it is applied also very good. But if you just pour the concrete or the grout, and you are not sure that it covered all the places. Maybe it went to one place and it did not go to the other. So in this case, you will not guarantee the accuracy of this grouting method. So if you can do it with accuracy, it is good, but if you can do it with accuracy, then it is better not to use this grouting. Now we go to an example. This example is exactly similar to what you have in your exam. So this is another revision for what we have studied. In this example, figure 1 shows a slope in material for which I have phi and c of the soil. C is 0 and phi is 25. Of course, I'm giving you here phi dash and c dash. It means that this is excluding the effect of water. This is the effective phi and the effective c of the soil. The soil is saturated. I have a gamma of 19.2. Then this is the gamma, the bulk or the saturated unit weight of the soil. Estimate the factor of safety against slip on a trial circle indicated in the figure. In this figure, he gave me this as being the critical surface. Of course, maybe somebody else would solve this problem proposing that the failure surface is like this, and really it is more logic for me that the failure surface is like this, not like this. But I cannot judge by just vision. I have to calculate. So this is that's why they said it's a trial circle. It's a trial circle because I'm not sure that this circle will give me the least factor of safety. Assume the pore pressure of water U is being 0.2 gamma H, where H is the mid-height of the corresponding slice. And he gave me here data instead of calculating it, because to calculate this, then I will have to study lots of things. I will have to know the angle here to the tangential, the angle of the tangent to this point, and the angle to the tangent to the mid here to this point and to this point. I have to calculate the height here and the height here and the height in the mid point, and so on. There are many calculations that needs to be graphically calculated. So usually it is given. So our slices are divided into just 3 slices. Of course, this is for understanding, but 3 slices is very, very small. In a slope like this, I would not take less than 6 or 7 slices to calculate it a little bit good. But this is just to understand. This is the start slice, and this is the end slice, and this is something in between, just for understanding. So the first slice, he gave me the height. You see here, this is the height of the slice, 1.3. This is slice number 1. Where is 1.3? It will be in the mid section. Slice number 2, the height is 2. It's here. From here to there, it is 2. Number 3, it is 1.5. From here to there, it is 1.5. Next thing is angle alpha. Alpha, it is given sometimes alpha, it is given sometimes phi. Anyway, it is the angle we need to differentiate. When we come to solve this problem, we have 2 values. Phi, which is the angle of internal friction. This is a soil property. This is something similar to what you have studied in your coursework number 1. But the other angle, whether they gave it to me in some cases, this alpha or phi, they are both, they refer to the same. It is the angle that is made by the tangent to each slice. If this is the midpoint of this slice, so there will be a tangent here. This angle, this is the angle of the tangent. So this is the angles minus 20, 15, 45. So here, you see this tangent, it is sloping in this direction. So here it is minus 20. Here it is 15. If you measure the slope of this, it will be less than the slope of this and in the opposite direction. If you measure the slope of this, it will be the higher slope, which is 45. Then the length of the base of the slice. Length of the base of the, for slice number 1, it is this length of this arc. Slide number 2, it is this arc, and slide number 3, this is the length of this arc. So these are the three lengths, and I need also to calculate the horizontal width. The horizontal width is the horizontal distance. I said that we usually use equal width of slices, so it is always here it is 4. Here we divided from here to there it is 4 meters, from here to there 4 meters, and from here to there it's also 4 meters. This ends up of the givens in the problem. I will just use this table for each slice. I will write what is given. This is what is given, and then we'll start calculating what I need to calculate based on my equation. This is the equation that I need to calculate to get the factor of safety. This equation includes W cosine phi, then I need to have something called W cosine phi, and then tan phi, all of the factors here, it should be included in this table so that I can just substitute for each slice all the parameters here, and then I will get a summation for all of the slices. Here I need W sine, this is the summation of W sine, and then I have W cosine minus UL multiplied by tan phi dash. Then I have to, this is calculated here, I get the summation of it here. Then the factor of safety is the summation of these values divided by the summation of these values. So it is 111 divided by 88. This will give me the factor of safety of this slope. I just said it very quickly. I'm not going to go further into it unless you study this again and we take a revision, and in the tutorial you will have a solution for an example similar to this. Thank you, and see you next lecture.